the efficiency of the buck converter is not 100%. And there are mainly three types of losses that we have in the buck converter. And the first one is conduction losses, which comes from resistances in all of the components that we have here. And so there are resistance in the switches. When there flows current, for example, through the switch, it flows through the resistor inside the switch, and then it generates heat or generate loss. But there are also resistances, for example, inside wires here. And then we also have, for example, so everywhere there are wires, we have some resistance. For example, inside the PCB or inside the conductors that we have. And then there are also some fuses, for example, on the input here. Maybe we have some relays, and maybe we also have some connectors on the input, on the output. So these also have some resistance, and therefore we will get some losses. And the second type of losses is associated with the switches. So it is losses that comes when you're switching. So one loss is, for example, driving the MOSFET itself. That takes some power. And the other loss is when you're switching itself. So for example, if you have a voltage over at this level, and then you have a current at this level. So let's say that this is current. Now, when you switch on the switch, so now it's off because the voltage over the switch is positive or it's high, and the current is zero, so there's no current flowing. But when you switch, the voltage falls and the current rises. And then you would get some losses in this region here, in the transient when you're switching. So this is a very simplified version of it. But like if to find the losses, you just multiply the voltage and the current in order to find the losses. And you will see that it's zero before we switch, and then it's positive when we switch, and then it's zero afterwards. So we generate some losses when we switch. And then we have the last kind of loss, and that is magnetics losses, which is only in the inductor here. So it comes from basically a changing flux. So the ripple of the current is linear with the flux density inside the inductor. So this could, for example, be the flux density. So the peak-to-peak flux density has a positive relationship with the power. So basically, the larger the peak-to-peak flux density we have, the larger losses we have. And same with current. So since the current has a linear relationship with the flux density, or it's not linear, but one could say it's linear in an ideal sense, then the larger ripple we have, the more losses we get inside the inductor. While the equation for this is more complex than that, it is actually very complex. So it depends on the switching frequency and also the peak of the flux density. But essentially, the more ripple we have, the more losses we have. And I didn't say it for the resistance, and I didn't say this for the conduction losses, but it is dependent on the current flowing through the resistance. So the power loss of the conduction losses is the resistance times the square of the current. So basically, the higher RMS current we have inside the circuit, the higher losses we have. So just to give you a visual representation, so here we have the switching, here we have the efficiency. So I will just go back to that later on. But here we have a numerical example of the losses. So at light load, basically where the current is low, then we know that the conduction losses are quite low because the current is low, right? And the switching losses are also quite low, while the switching losses are relatively low because they also depend on the current. So the switching losses depend on the current, the voltage, the switching frequency, and also the temperature. So it is also lower. While the core losses, the magnetics losses, are quite high because they are independent of the current, right? So they depend on the ripple of the current, not the magnitude of the current itself. while at a heavy load, it is kind of like the opposite. So here, the conduction losses is way higher because the current is way higher, and we square the current. While the switching losses is higher, it's significantly higher, but it doesn't increase as much as the conduction losses because it scales with the current, but not so much because it's more dependent on, for example, the switching frequency. And then the core losses just stays the same because it's not dependent on the magnitude of the current. So this is a very ideal numerical example. But there are some small things that are not correct here, but in order to cover that, we need to go much more in detail. So that is why we get this type of an efficiency curve. In the beginning, it rises very quickly, and that is due to the magnetic losses. So it's very high due to the magnetic losses, while it starts to decrease afterwards because of the conduction losses increases. And that is why we get a peak efficiency at a relatively lower point. And you can design this buck converter to have a peak efficiency at wherever you want. For example, if you usually operate at, for example, 500 watts, you should have the peak efficiency at 500 watts. But if you usually operate here, then you should get it there. And if you usually operate at maximum power, then you should want the efficiency to be as high as possible at the maximum power. But this is a trade-off between the size of the converter itself, the cost, and also the efficiency. And the reason why we actually care about efficiency is mostly because it generates heat. So the more heat the converter produces, the more heat we need to extract from the converter. So therefore, it is beneficial to have a low efficiency as possible so that we reduce the wear on the components and also reduce the power we need to spend on getting the heat out of the system. So that is also why having a higher efficiency on higher power levels is important, because on higher power levels, the efficiency have more to say, because that is in watts much more. Now, in the next video, we will go through how you can control a buck converter. And if you're interested in this course, then you can go into the link in the description.